This is an alternative way to generate a function. Instead of finding every point on the graph, here we are drawing all the tangent lines first. Hidden in this process lies an interesting duality between points and lines. A duality that also occurs between fundamental quantities found in both classical mechanics and thermodynamics. By the end of this video, you will see that all these dualities are really just basic applications of one simple yet powerful math trick known as the Legendre Transform. The Legendre Transform was developed in 1787 by the French mathematical physicist Adrien Marie Legendre. Just 50 years later, in the mid-1830s, William Rowan Hamilton used it to introduce an entirely new formulation of classical mechanics. A formulation that built upon Newton and Lagrange's earlier work and used as its starting point the Legendre transform of the Lagrangian, better known as the Hamiltonian. After another 40 years or so passed, in 1878, Josiah Willard Gibbs would use Legendre's transform to generate three extremely useful thermodynamic quantities out of the internal energy. Amazingly, what makes all of this possible is just one main idea. All the information about a function is stored in its tangent lines. Or rather, to be more precise, the y-intercepts of its tangent lines. How is this possible? And for which type of functions is this true? We'll discover the answers by considering a few basic examples. Let's start with the function f of x equals x squared. Now, what kind of information is actually contained in this function? What we have here is the knowledge that for any value of x, we can always assign a specific value f of x. Our goal will be to transform f from depending on x to a new function that depends on some other variable that we'll call p. But we want to do it in such a way that no information is lost in the process. The way we'll do it is through the derivative. If we take the derivative of f, we get a new function that now specifies the slope of the tangent line at every point x. We call this new function p, which is dependent on x. Now, in this specific example, for every x, we get an entirely unique value of p. This means that there's a one-to-one correspondence between p and x, which allows us to consider yet another function x of p. So we have two ways of viewing things here, either p as a function of x or x as a function of p. We can then plug x directly into f, making f now dependent on p. It seems like we've succeeded, right? We have transformed f from a function that depends on x to a new function that depends on p, without losing any information. Not quite. Look at what happens if we consider the function f of x equals x minus d squared. If we apply the same type of reasoning, so we first find its derivative, solve for x as a function of p, and then plug back into f, we find the exact same result. Whatever value we plug in for d here will always lead to the same end function. The information about d is lost in the procedure we're currently following. The reason this occurs is because we've only been considering the tangent lines of each function, which turn out to be the same everywhere, just shifted. Fortunately, there is a closely related quantity that is able to capture the uniqueness of each of these functions, and that is the y-intercepts of the tangent lines, which you can see actually do differ depending on the original function. So taking this into account, we'll now call this line f, which is just the line from x to f of x, and also define the value g as the negative of the y-intercept. Then recalling that p was just the derivative, we can use simple geometry to relate g and f. Finally, we arrive at a new function that truly retains all the information of the original. And this new function is the Legendre transform of f. This is the general form of it. If we apply it to our family of functions we've been considering, we get the following. As you can see from the equation on the right, we have no longer lost information about d. It is only when d equals 0 that the equation on the right reduces to the one on the left. Since we've now incorporated info about the y-intercepts of tangent lines, each of the original functions of x maps to a unique function of p. And because no information has been lost in this updated process, we can also find the Legendre transform of g and arrive back at the original f. We now truly have two ways of expressing the same information. One that depends on the variable x, and the other that depends on the variable p, providing a beautiful duality between points and lines. So we've discovered a way to apply this transformation to a whole family of functions of this particular form. But what other functions can we apply it to? To motivate the answer to this, we'll consider one more basic example. Let's see what happens if we try to apply the Legendre transform to the function f of x equals x cubed. We follow the same steps as before. First, we find the derivative and call it p of x. Then, we try to solve for x as a function of p. Immediately, we run into a problem. This is not a function. Any value we plug in for p will result in two different values for x. What this means is that there are many pairs of points that have the same slope. We can see this visually if we plot the derivative. With the exception of the origin, we are always able to find 2 points that have the exact same value. And in terms of f of x, these values correspond to producing the exact same slope for 2 tangent lines. This illustrates the key thing we need in order to be able to find the Legendre transform of a given function. We need all the slopes of tangent lines to be unique. And this will occur if the function's derivative is essentially always decreasing or increasing. The technical math term is that it must be monotonic. And there's also an entirely equivalent way to say this in terms of the original function f. In order for a function f to have a Legendre transform, it needs to be convex, meaning that if you connect any 2 points on the curve, the line is always on the same side of the curve, whether that's on top or below. As soon as you find 2 points where this behavior switches, it automatically means that the function is not convex, and there's no way to perform a Legendre transform of the function. So in general, given any convex function, we can always find the Legendre transform of it by applying this formula with just 3 simple steps. And since this always produces a convex function g, we are guaranteed to arrive back at the original f whenever we apply the Legendre transform to g. Now, everything I've been saying applies to convex functions of a single variable. This can be useful at times. However, when generalized to functions of more than one variable, it becomes much more useful and applicable. All it requires is to apply the product rule to what we've already learned. For any pair of variables x and y, we can multiply them together and consider a tiny change in their value or differential. By the product rule, this equals x dy plus y dx. Similarly, if we have a function that depends on both x and y, then we can write its differential as follows, where this term means we take the partial derivative of f with respect to x while keeping y fixed, and this one is the partial derivative with respect to y while keeping x fixed. We can write this in a nicer form if we call the first one u and the second one v. Now what we'd like to do is to see if it would be possible to construct a new function g that instead of depending on x and y, it rather depends on u and y. So its differential will be something times du plus something times dy. And in order to find this, the trick is simply to subtract f from u times x, which is really just the definition of the Legendre transform we found earlier. If we then take the differential of this, we get dg equals u dx plus x du minus df. Substituting for df, we find the following. And since the differentials here are of y and u, these are the two independent variables of our new function g. The final step is then to just use this bottom equation to solve for x in terms of u. If we do that, then we can replace the x's above with terms that contain u instead. If we follow these steps for a convex function f that depends on x and y, we are guaranteed to arrive at a function g that is dependent on u and y. Using similar reasoning, we can also switch to a new function of x and v, or a function of u and v. So depending on how many independent variables the original function depends on, there will be 2 to the n different functions we can transform to. In order to make this sink in and be a bit more concrete, we'll now turn our attention to how this shows up in physics. Our first example will be from thermodynamics. One of the fundamental quantities in thermodynamics is the internal energy U of a physical system, which depends on entropy, volume, and the number of particles. As a differential, the relations between all of these is expressed as follows. Now there's another thermodynamic quantity called the Helmholtz free energy, which is defined by subtracting T times S from U. But this is really just a Legendre transform of the internal energy. In physics, the sign convention is sometimes reversed in order to make sure certain physical quantities have the correct sign. So if we take the differential of F now, we can see that dF equals du minus Tds minus S dt. Substituting for du and canceling terms results in the following, which means that f is a function of v, t, and n. Now remember, the Legendre transform simply swaps variables and allows us to keep all the same information contained in the original function. So whatever physics is present in the internal energy equation, the exact same physics is captured by the Helmholtz free energy equation. It's just that we now have 2 options to use based on what our experimental controls might be. If we can control the entropy and volume, then this is the equation to use. But if we instead can control the temperature and volume, we have this equation. We can take one more step in this process by doing another Legendre transform to swap the volume for pressure. This is done by subtracting negative PV from F. We call this G, the Gibbs free energy. Its differential is the following, and substituting for dF results in this expression. So the Gibbs free energy depends on temperature, pressure, and particle number. Doing another Legendre transform, subtracting negative S times T from G, we can get yet one more expression called the enthalpy. The differential is then this. And again, substituting, we get the following. So the enthalpy is a function of entropy, pressure, and particle number. And finally, after applying one more transform, we arrive back at the internal energy. Let's now take a moment to consider what all this means and appreciate just how powerful the simple math trick of the Legendre transform can be. We have 4 different expressions here that all contain the same information about the physics of a thermodynamic system. All we need is to know just one of these, and by the Legendre transform, we can generate the rest. And in each case, we have different control variables. So depending on your experimental conditions and what you're able to control, the Legendre transform allows you to start from any of these and arrive at the one you actually need. These equations also tell us that in a state of thermal equilibrium, if the entropy, volume, and particle number of the system are constant, then we know that internal energy is at a minimum. Similarly, if the temperature, volume, and number are constant, then the Helmholtz free energy is at a minimum. And of course, the same type of reasoning applies to the Gibbs free energy and enthalpy. Let's now consider how the Legendre transform shows up in classical mechanics. After Newton's initial formulation of classical mechanics with vectors, there were two alternative versions developed by Joseph Louis Lagrange and William Rowan Hamilton. These formulations removed vectors entirely and instead turned solving physics problems into pure algebraic manipulation. The starting point for Lagrangian mechanics is a quantity called the Lagrangian, which is a function of two variables, q and q dot. The starting point for Hamiltonian mechanics is a function called the Hamiltonian, which is defined by subtracting L from p times q dot, where p is the so-called generalized momentum, defined as a partial derivative of L. And again, this is just a Legendre transform. By swapping p and q dot, we are able to transform from a function dependent on q and q dot to another dependent on q and p. You can see exactly how this happens with a very basic example. Imagine a ball in free fall. So it's only under the influence of gravity. If q is in this direction, then its Lagrangian is given by the following expression, which implies that the Hamiltonian is given by this expression. Then, using the definition of generalized momentum and reducing, we really can express h purely as a function of q and p. Going back to the more general case, we can use this expression to write down the differential of h. But L is a function of q and q dot, so dl should equal the following. And since h is really just a function of q and p, its differential can be similarly expressed as follows. Canceling and setting like terms equal to each other, we discovered the famous Hamilton's equations. These are the equations of motion for a system described by Hamiltonian mechanics. They contain the exact same information that is contained in the Euler-Lagrange equations, which is how you get the equations of motion in Lagrangian mechanics. And just as we went from the Lagrangian to the Hamiltonian, we can also apply the Legendre transform to the Hamiltonian and arrive back at the Lagrangian. So this seemingly simple math trick proves to be extremely powerful. It provides a very useful way to swap different variables and still keep all the information about a function, truly capturing the duality between points and lines, various thermodynamic potentials, and even two different formulations of classical mechanics. If you've stuck around to the end, I first want to say thank you for watching this video and for already supporting the channel. I'd also like to invite you to consider joining my new Patreon community. I'll be posting there regularly to get your feedback. So if you want to weigh in on video topics, animations I'm working on, or even thumbnail design, that's the place to go. You'll also get early access to content, help shape final edits, and most of all, contribute to making higher math and physics accessible to more people. So if you're at all interested and financially able to do so, please consider joining. Thanks again, and remember to always abide by reason.